Welcome to another deep dive into the fascinating world of biology. Today we're going to be talking about angiogenesis, basically how our bodies create new blood vessels.
Oh, wow.
And this is a vital process for life, everything from like development in the womb to healing wounds. But as we'll see, it can also be kind of hijacked by things like cancer cells that are trying to, grow and spread. So
Yeah.
to guide us on this journey today, we have an article from Assay Genie. It's titled VEGF-A VEGFR-2 signaling, decoding the blueprint of angiogenesis for therapeutic insights. So those names sound pretty technical, but they're really just the stars of our show today. Can you help us understand who these players are and what roles they play?
Absolutely. It's really all about communication. You can think of VEG-A, which stands for Vascular Endothelial Growth Factor A,
Right.
as a signal flare that's sent out by cells that need a blood supply. It's like they're saying, hey, we need more blood vessels over here.
Oh, so VEGFR-2 is like the lookout tower that's receiving that signal.
Exactly. VEGFR-2 or VEGF receptor 2. It sits on the surface of cells that line blood vessels. These are called endothelial cells. And it's the main receptor that picks up that VEGF-A signal. And when it does, it sets off this chain reaction, this beautifully orchestrated process that the article breaks down into 5 key steps.
5 steps, huh? Almost sounds like a dance. So what happens first?
Well, first things first, the signal flare VEGF-A has to reach the lookout tower VEGFR-2. So that's our first step, which is called initiation. When VEGF-A binds to VEGFR-2, it's like flipping a switch. It activates the receptor and sets the whole process in motion.
Okay, so we flip the switch. What's next in this intricate dance?
So the next step is called elevation. And this is where VEGFR-2 gets to work modifying itself. So it starts attaching these little phosphate groups, almost like adding sticky notes to a file. And this is what allows other molecules to attach and join the party. This process is called phosphorylation, and it's a key step in transmitting the signal.
So it's kind of like VEGFR-2 is setting the stage for this cascade of events, creating these docking stations for other molecules to come and join the fun.
Exactly. And that brings us to our third step called harmony. And now things start to get really complex. All of those invited molecules trigger a cascade of downstream pathways, each with its own role to play.
I see. The article mentions PLC, PI3 kinase, and MAP kinases. Can you give us a simple way to understand what those pathways are all about?
You can think of it this way, like an orchestra. Each of those pathways is like a different section, playing its own part in the symphony of angiogenesis. So PLC is our drummer, setting the rhythm for cell movement through calcium signaling. PI3 kinase is kind of like our construction crew, ensuring cell survival and growth. And then MAP kinases are the organizers, controlling cell growth and specialization.
Wow, so there's a lot going on behind the scenes.
Right.
But ultimately, all this molecular music leads to changes in those endothelial cells, right? What does that look like in the expression stage?
You got it. So the endothelial cells, energized by this symphony, start changing their behavior. They begin to proliferate, meaning that they multiply to create more cells. They also become more migratory, like a group of dancers moving towards the source of the music, which is that VEGF-A signal. And finally, they become more permeable, meaning it's easier for things to pass in and out of the blood vessels. And this is crucial for delivering nutrients and oxygen to that growing tissue.
It's amazing how all these players come together to make sure new blood vessels can form. It really is like this perfectly choreographed ballet,
Yeah,
culminating in our final step culmination.
exactly. All those changes we've been talking about, the proliferation, the migration, the increased permeability, allow those endothelial cells to form these new networks of blood vessels, completing the process of angiogenesis.
Wow, this is pretty intricate stuff. But before we get even deeper into the science, I'm kind of curious, why should we care about angiogenesis in the first place? It seems pretty technical.
Well, it might seem technical, but it's actually fundamental to life as we know it. Angiogenesis isn't just about creating blood vessels. It's about building and sustaining life. Without it, none of us would exist.
Oh, yeah. Now that you mention it, I remember learning about how crucial blood vessels are. But I never really connected it back to this process of angiogenesis. How exactly does it contribute to keeping us alive and functioning?
Well, think about it. During embryonic development, angiogenesis is what allows that circulatory system to form. It creates that intricate network of blood vessels that transport oxygen and nutrients to every cell in that developing embryo. Without angiogenesis, we simply wouldn't develop properly.
So it's not just about having blood vessels, it's about building them in the first place. That makes sense. But what about after we're born? Does angiogenesis still play a role?
Absolutely. Even after we're born, angiogenesis continues to be essential for growth and repair. Every time you get a cut or a scrape, angiogenesis is what allows your body to heal. New blood vessels grow into that damaged tissue. delivering oxygen and nutrients that are essential for repair.
It's like our body's own little internal repair crew, rebuilding those vital pathways wherever they're needed. I had no idea it was so involved in such a constant everyday process. Are there other examples of angiogenesis at work in adults?
Certainly. Another great example is the menstrual cycle. Each month, the lining of the uterus thickens in preparation for a possible pregnancy. And this thickening is actually driven by angiogenesis if a pregnancy doesn't occur. That lining is shed and the cycle begins anew.
Wow. I never realized that angiogenesis was so central to such a fundamental biological process. It really is about so much more than just blood vessels. But I have a feeling this story isn't all sunshine and roses, right? There's a darker side to angiogenesis too, isn't there? Something about cancer.
That's a great observation. While angiogenesis is essential for life, it can also be exploited. And that's where things get really interesting and a little bit scary. Cancer cells, in their relentless drive to grow and spread, have figured out how to hijack this process for their own benefit.
This is where it gets really interesting. Stay tuned, because when we come back, we'll explore how this very pathway, this blueprint of angiogenesis, is being targeted to fight one of humanity's biggest challenges, cancer. Don't go anywhere.
Welcome back. Before we went to the break, we were talking about angiogenesis as this beautiful, intricate dance of life. But as we hinted, this dance can take a darker turn when it comes to cancer.
Okay, so I'm ready to learn about the villain in this story.
Yeah.
How do cancer cells manage to exploit something as essential as angiogenesis?
Well, imagine a tumor growing inside the body. It's like a city that's rapidly expanding, needing more and more resources, oxygen, nutrients, a way to get rid of waste.
And of course, all those resources are delivered through blood vessels.
Exactly. As the tumor grows, it starts sending out these distress signals, and one of those signals is, you guessed it, VEGF-A. It's like the tumor city is putting out a desperate call for new roads and infrastructure.
So the tumor is basically tricking the body into growing new blood vessels right into its own heart. They've got sneaky.
That's exactly what's happening. It's called tumor angiogenesis, and it's a key factor in how cancers grow and spread. By hijacking the VEGF-A VEGFR-2 pathway, tumors can essentially build their own private supply lines, bringing in everything they need to thrive.
It's amazing and terrifying at the same time. This makes me wonder, if we understand how this pathway works, can we use that knowledge to fight back against cancer? Can we cut off those supply lines?
That's the brilliant part. Understanding the enemy's tactics allows us to develop counter strategies, and that's where the therapeutic insights mentioned in the article come into play.
Okay, I'm all ears. How are scientists targeting this pathway to develop new cancer treatments?
Well, there are several approaches being explored. One of the most successful so far is using drugs that act like signal jammers, blocking VEGF-A from reaching its receptor.
So instead of letting the tumors call for new blood vessels go through, we're scrambling the message.
Precisely. These drugs are like molecular shields, preventing VEGF-A from binding to VEGFR-2 and activating the pathway. The article specifically mentions a drug called bevacizumab.
Bevacizumab. That name rings a bell. What can you tell us about it?
Bevacizumab is a monoclonal antibody. It's a type of drug that's designed to target a very specific molecule. In this case, it targets and neutralizes VEGF-A. It's been remarkably successful in treating various types of cancer, including colorectal lung and brain cancers.
Wow, so this isn't just theoretical. It's actually being used to help people fight cancer right now.
It is, and that's just one example. Scientists are also developing drugs that directly block VEGFR-2, the receptor itself.
So instead of scrambling the signal, we're making the lookout tower unresponsive.
Exactly. The goal is the same, to disrupt the pathway and prevent the tumor from building its blood supply.
It sounds like there's a whole arsenal of weapons being developed to target angiogenesis in cancer. This is really encouraging. But what about the potential downsides? Messing with something as fundamental as blood vessel formation must come with some risks, right?
You're absolutely right. There's always a balance to strike. Angiogenesis inhibitors, as these drugs are called, can have side effects, some of which can be serious.
Like what kinds of side effects?
Because angiogenesis is involved in so many processes, blocking it can interfere with things like wound healing. So people taking these drugs might experience slower healing times. There's also a risk of high blood pressure and even bleeding because blood vessels become more fragile.
So it's a trade-off, weighing the benefits against the risks. But it sounds like in many cases, the benefits outweigh the risks, especially when we're talking about treating life-threatening cancers.
That's the key. It's all about personalized medicine, finding the right treatment for the right patient at the right time, and having a deep understanding of the VEGF-A, VEGFR-2 pathway is helping doctors make those informed decisions.
You know, I'm really struck by how this conversation has evolved. We started with what seemed like a pretty technical topic, blood vessel formation,
Hmm.
and now we're talking about cutting-edge cancer treatments. It really highlights how fundamental biology is to solving some of our biggest medical challenges.
Absolutely. And what's so exciting is that we're really just at the beginning of this journey. As scientists continue to unravel the mysteries of angiogenesis, who knows what other applications might be possible in the future?
Ooh, that's a great point. What other doors might this research open?
Well, for starters, imagine being able to harness angiogenesis to accelerate wound healing. This could be a game changer for people with diabetes, who often struggle with slow healing wounds.
That would be incredible. What about using it to treat heart disease?
That's another area with huge potential. If we could stimulate the growth of new blood vessels in damaged heart tissue, it could revolutionize how we treat heart attacks and other cardiovascular diseases.
This is where it gets really interesting. What if we could even regenerate entire organs
Hmm.
using our knowledge of angiogenesis? The possibilities seem endless.
I know, right? But hold on. Before we get too carried away with futuristic scenarios, there's one more crucial point from the article that I think we need to address.
Okay, bring it on. What have we missed? Okay, so what's this crucial point we got to cover?
Well, it's kind of like a reality check. The article emphasizes that. While targeting the VEGF-A VEGFR-2 pathway has incredible promise, there's still a lot we just don't know. It's a much more complex system than we initially thought.
I could see how that might complicate things. Why is it so complex, though?
Yeah.
What are some of the challenges that researchers are facing?
Well, it's not as simple as, VEGF-A binds to VEGFR-2 and boom, new blood vessels appear. There's a whole network of other molecules involved, other members of the VEGF family, co-receptors, feedback loops. It's like this tangled web of signal.
So instead of just a simple on-off switch, it's more like a control panel with dials and buttons and feedback mechanisms. No wonder it's taking scientists a while to figure it all out.
Exactly. And to make things even trickier, the pathway can behave differently depending on the context. What happens in a developing embryo might not be the same as what happens in a wound or a tumor.
Oh, so context matters.
That makes sense.
But it also kind of adds another layer of complexity for researchers. The ones trying to understand and manipulate this pathway?
It does. And then there's the challenge of unintended consequences. If we block VEGF-A to stop tumor growth, what other processes might we be affecting? Remember, angiogenesis is essential for a lot of normal bodily functions.
Right, it's a delicate balancing act. We don't want to throw off the entire system just to target one specific problem.
Precisely. So while the therapeutic potential is huge, we really need to proceed with caution.
Yeah.
More research is needed to fully understand this intricate signaling network and to develop more targeted therapies with fewer side effects.
This has been such an eye-opening deep dive. We started with what seemed like a very basic biological process,
Yeah.
and we ended up exploring cutting-edge cancer treatments, and even the potential for regenerating organs. It's amazing how much one pathway can impact human health.
It really is. And the journey of discovery is far from over. As scientists continue to explore the intricacies of the VEGF-A VEGFR-2 pathway, we can expect even more groundbreaking insights and therapeutic advancements. In the years to come,
That's very exciting to think about. So to sum up what we've learned today, the VEGF-A VEGFR-2 pathway is a powerful force in both health and disease. It's essential for life. But it can also be exploited by cancer cells. Scientists are hard at work, developing drugs that target this pathway. And this offers hope for new and more effective cancer treatments. And who knows what other amazing applications the future holds.
exactly. And one final thought I'd like to leave with our listeners. The human body is an incredibly complex and interconnected system. What might seem like a small or even obscure biological process can have far-reaching consequences. So next time you hear about a scientific discovery, no matter how technical it sounds, remember that it could hold the key to understanding and treating some of humanity's greatest challenges.
That's a great point to end on. Thanks for joining us on this deep dive into the fascinating world of angiogenesis. We'll see you next time, when we explore another intriguing scientific frontier. Until then, stay curious.